The next talk is on performance analysis of deep learning models, deep learning workloads in a composable system by Dr. Kaoutar El Maghraoui from IBM Research. Kaoutar, let me make you the presenter. Give me 1 minute. Yeah, you should be able to start sharing in a minute. Great. So Dr. Kaoutar El Maghraoui is a principal researcher at IBM Research. She leads the work in the AI department, AI research department on the AI Hardware Center, performance analysis, characterization of workloads, as well as the design of analog hardware simulators and so on. Right. Kaoutar, the floor is all yours.
Thank you so much, Jairam. Can you hear me?
Yeah.
Okay, great. So I hate to be between the audience and the end of the workshop. So thank you so much for staying all the way to the end to listen to our talk. So I'm presenting this on behalf of our team from the AI Hardware Center. So this talk will talk about, the analysis that we did on deep learning workloads on composable systems. And if you've seen Dr. Chris Carruthers' excellent talk on also the composable system, it was really a great introduction and nice segue to this talk. So before I jump into the talk, I also want to introduce briefly the IBM Research AI Hardware Center initiative, under which this work is being conducted. So this is a research collaboration and center with the purpose of driving next generation AI hardware. And this center was launched, in the February of 2019. And a lot of key initiatives here centered around innovating and developing next generation AI hardware accelerators, including innovations, at cores and architectures, leveraging things like reduced precision for AI, reduced precision accelerators, heterogeneous integration, looking also at analog AI. And Dr. Rania Khalaf also gave a great introduction to what's happening in that space. And looking also at, the end-use test bed, which is the work that I and my colleague Lorraine Herger are co-leading in this space here. And the composable server is one of the infrastructures that we're studying, but also we're giving as an R&D tool to our AI Hardware Center partners and clients. So as part of the AI Hardware Center end user testbed, we have a bunch of infrastructure that we're evaluating and through which we're also allowing experimentation and evaluation of next generation AI hardware accelerators. And this brings us to the composable testbed, which is one element here that allows us to do experimentation with various system level topologies and configurations. So why composable systems? Dr. Chris Carruthers from RPI gave also very great motivations around, the need for having composable systems. So as we all know, today's data centers, they often suffer from resource wastage and underutilization across a host of workloads. And this is often due to the way these systems are configured and designed, because the systems here, the resources are delivered in fixed ratios. Once you design a system all the way down, to the processor level, the resources are wasted. You have a fixed number of acceleration versus computation versus storage, and it's very hard to cater to a variety or dynamic range of workloads that have different characteristics and different demands. And often, enterprise settings, these prolonged underutilizations, they imply failure. They also imply a lot of wastage, and of course translates to costs and inefficiencies. So, however, composable systems, they promise, this optimal cost performance across multiple workloads. And here the idea is you want to carve out systems that in a dynamic way that's tailored to a different variety of workloads. In the picture here, you have, for example, traditional workloads where we have the workloads needs communication versus computation. No acceleration here is needed. And then as we move more and more towards, for example, AI workloads or large scale data workloads, the need for acceleration increases, the need also for communication increases. So how do we build systems that can dynamically adjust to these varied workloads? And that's, where the concept of the composable system came in, composable versus traditional systems that have fixed ratios of compute, memory, input, output, I/O, and so on. Whereas in composable systems, we have this high performance interconnect that enables plug-in different resources. So think here that you have a resource pool that is comprised of multiple system level elements like FPGAs, NVMe drives, GPUs, memory elements, networking elements, CPUs, and so on. And through this design, we can provide operational efficiencies because you can draw enough resources from each component depending on the workload that you need to run. And here, the system can be stood up dynamically, can be torn down also dynamically, depending also on the workload that you're running. And one also of the key advantage of this design is this decouples the life cycle of different resources. In the earlier talk that Professor Chris gave, he talked about this and then he showed a simulation that shows the benefit of having a system like this. In this talk, actually, we have designed and have an actual implementation of a composable system. And what we have done is we have tried to evaluate the performance of this composability or the overhead on actual deep learning workloads. So that just shows when this composable system is more appropriate. Here you can have a large collection of I/O and acceleration devices available to multiple compute hosts. Individual systems can be dynamically configured to user specifications. And also, the design that we have done, and actually this prototype and implementation, we've done it with a partner vendor called H3 Platforms, who helped us, put together and implement the system. And here, when we have evolving workloads, as in the case of cognitive applications today, flexibility becomes really more valuable sometimes than even resource efficiency. And also when we have to deal with a range of application types, especially in cloud settings and data centers. So users here can receive isolated, precisely tailored, and cost-effective systems which can evolve, as the business need or the workloads are evolving. So this shows, for example, an example here where we can see how a composable system can be configured to tailor to two different applications. For example, we have an application here where we call here CPU offload mode, where we have a certain need for acceleration versus communication versus CPU. And the red elements here, it means the CPU elements like the servers. And then the yellow elements, these are the accelerators, for example, GPUs. And the orange elements here are the storage devices. And here you can see that the system can be partitioned in a way that here we give less acceleration to the application on the left and more acceleration to the application on the right. I mean, just for the purpose of simplifying this figure, storage also are used here. We just didn't want to clutter the figure here. So that's just a very simple example. So what's happening in the space here in terms of related or existing work, the concept of composability is not new. It has been around for many years. Things, for example, like the resource pooling that is happening in providing an SMP with shared memory. There's also the concept, with logical partitions and dynamic logical partitions that IBM also introduced in power systems and through the AIX operating system. The blade servers in the late 1990s, and also the very good example that Professor Chris provided through the Blue Gene system. So all of this tried, to provide some level of composability where resources are grouped or virtualized together, and then with the goal of simplifying management and allowing different levels of upgradability for the hardware. There's also a lot of work that has happened and also happening with respect to disaggregated memory, especially with focus on optically connected memory due to its fast interconnect. And our design here is more focused on pushing the sharing to the bare metal hardware, which is really gives much better flexibility and performance. So this shows basically the prototype that we have, our composable implementation. So the way this is done, hosts are connected to this testbed. You see here a real picture of a composable testbed. So the hosts are connected through a host bus adapter or HBA, and it has two drawers, each with 8 PCIe slots. And the core of this is a PCIe fabric that allows basically the communication between the different components in the system. And then the user configures the drawer basically to connect to a specified host and also the connected devices. Here, the designs allows all the devices to appear native to the host as if they are part or integrated with the host. And here it just shows an example topology of the Falcon switch, which was fabricated by H3 platforms in collaboration with us. You can see here, for example, multiple hosts can be attached with the HBA through the Falcon. And then here we have two drawers, and then the baseboard. And the line 8, we have the PCIe Gen 4 switches, and through which, the different components can be connected. Okay, and underlying this, there is a full sophisticated routing mechanism that happens between the different elements. You can see here, for example, the PCIe exposes ports through which, GPUs, NVMEs, etc., hosts and so on can connect. And then this also provides, the way this is designed, that it can also provide peer-to-peer direct communication between the devices itself, between GPU and GPU across maybe the host or through the fabric or the PCIe switch, which gives also bypassing the CPU. So here the CPU is not the one controlling or coordinating, which gives also much better performance. And there's also fault tolerance built into the design here. So I'll just quickly describe the current configuration that we have for the test bed that we're using for the performance evaluation. So here we have the Falcon that we call the Falcon system with the PCIe fabric here. So we have two Falcon switches, and then we have two hosts. We're using here super micros, and they're attached. Each one of them is attached to a Falcon. And there are actually different modes through which you can configure this system. You can also attach two hosts to one Falcon. I'm not going to go into the details of the different modes of operation. There is advanced mode, and some of these modes allows, greater flexibility in terms of hot plugging and things like that. We don't have time to go into all of those details. And so overall, the system provides a total of 44 x86 CPUs. Each one of these hosts has 8 locally connected GPUs with more than 700 gigabytes of memory. And this, you can see here, these are like this, like the Falcon. It shows the different ports here through which you can connect different devices. So for the purpose of the study that we have done, we wanted to evaluate representative deep learning benchmarks. And the way we selected those benchmarks is basically to cover a wide range of model size, computation to communication ratio, pre-processing steps, and also different types of neural network architectures like convolutions and transformers. So, I mean, this table here on the right shows the benchmark that we have evaluated. We have MobileNet v2, ResNet 50, YOLO, BERT base, and BERT large from the NLP space. And so the goal here is we want to analyze the sensitivity of these applications to the hardware resource disaggregation. So because the way we configure the system, we have the host that has locally attached GPUs, but there are also GPUs that are attached to the Falcon. So we wanted to see if that really makes a difference for the application level performance. And this is a real system, so we're not doing this in a simulated manner. We're running this directly on a composable hardware. And we also want to exercise various mode of operations for the system, evaluate the overhead of the PCIe switching. And I mean, all of this is kind of building a methodology that allows us to study not just deep learning, but a variety of applications and build profiling methodologies to showcase the value of hardware disaggregation when it makes sense, when it doesn't make sense, and so on. For the purpose of the experimentation setup, we use only one host here, and each host here has access to a total of 8 GPUs. 4 of them are attached to the host directly, and 4 of them are attached to the switch or to the PCIe fabric here. And so this setup gives us a host total of 16 GPUs. But we're only used, I think here, 8 GPUs local and 8 GPUs Falcon attached. And so you can see here the different configurations that we have tried. Actually, we've tried 8 local GPUs with local storage. We also have storage that's attached directly to the host and storage that attach through the Falcon switch. And we have basically configured these different configurations: local GPUs, meaning all the GPUs attached with local storage; hybrid GPUs, meaning half of the GPUs are through the host itself and half through the Falcon system; Falcon GPUs, meaning all the GPUs are attached to the Falcon switch; a local NVMe, meaning that the storage is locally attached to the host; and Falcon NVMe, meaning that the storage is attached to the Falcon switch. Basically, this what it shows. What we've done, we've measured we've done training for all of these benchmarks on the composable system with these various configurations. And this just shows basically the GPU utilization profile for these different benchmarks. And we've run all these benchmarks to conversion until the training finished, just to get an idea how the resources are being utilized in general. So this just shows one of the plots here. So the models here, we were using PyTorch, distributed data parallel with NVIDIA Nickel backend. And in this approach, multiprocessing is used to duplicate the model across multiple GPUs, each of which is controlled by one process. And so here, we can see here that there are basically GPUs are highly utilized, but of course, at every epoch, there are all these synchronization overheads, which basically are due to the periodic synchronization and checkpointing of the models. That's why you see these drops in the GPU utilization. So looking at the overhead of the PCIe traffic, or the what we call composability overhead here. So what we've done here, we've measured the performance, and also we've measured the traffic that's happening through the PCIe switch using the hybrid GPUs, meaning half of the GPUs through the host and half through the Falcon switch, and all the GPUs through the Falcon switch. And you can see here, model gets larger, of course, we see more traffic happening in the PCIe fabric. So the figure on the left shows the amount of data that has been exchanged using the hybrid and then the Falcon configurations. You can see here that we also measure the latency and the bandwidth within the Falcon GPU to GPU bandwidth and latency and the protocols that are used. You can see here, local to local, meaning the GPUs are local to the host, NVLink is used. Falcon to local or Falcon to Falcon, meaning this is the hybrid, the one in the middle, and then this is the pure PCIe switch connection. You can see here the difference between the bandwidth. So of course, local to local has much higher bandwidth, and Falcon to local and Falcon to Falcon is less bandwidth, and that's what affects also, you see, how this impacts the performance. So the PCIe traffic, especially for larger models like BERT large, here on the Falcon GPUs was 76.43 gigabits per second, which is about 19 times higher than what you see in MobileNet V2 and in ResNet 50. And of course, this is expected because there are many more parameters and a lot of data being exchanged here for these larger models. Looking at how this overhead is impacting the training time. So what this figure shows is the relative training time compared to using the host with only local GPUs for all of the deep learning benchmarks. And what we notice here, as the model size or the number of model parameters increases, we start noticing the impact of the PCIe switching. So in these cases, the models need to exchange very large amounts of data, and the inter-GPU communication becomes a bottleneck here. For smaller models, for example, MobileNet, ResNet 50 here, there isn't much overhead in terms of the PCIe switching. And in general, what we notice is the training is less than 7% slower than when using the all local GPU configuration. However, for the NLP benchmark, we notice that there is overhead increased by this PCIe switching, and this is mostly attributed to the large number of parameters. And looking at the storage performance. So here, what we're doing is we want to evaluate the impact of attaching an NVMe storage device to the Falcon switch, basically disaggregated or the local. And here, actually, what we notice is using NVMe storage has, improved the performance, especially that, this helps a lot with the data loading speed. We can see that for BERT and YOLO as well. And the overhead of PCIe switching here through the Falcon is small in this case, is pretty much negligible. So in addition to that, we've also done some additional software level optimizations just to see how much this will impact in this composable setting. And what we see here, what we've done is we evaluated things like PyTorch distributed parallel, PyTorch distributed data parallel, the Facebook sharded optimization, and also mixed precision. And we noticed that mixed precision training, which is not actually surprising, provides significant speed up as it allows reducing the memory footprint during training while retaining the same accuracy. In addition to PyTorch, distributed data parallel, the PyTorch also provides the data parallel mechanism when training on one node with multiple GPUs. And of course, here, the distributed data parallel gives much better performance in our case. The sharded optimization also further optimizes memory and is especially useful for large models. It tries to eliminate memory redundancies and hence, it reduces the low communication, try to retain low communication volume as shown in the figure. So this also, helps kind of mitigate some of the overhead that we're seeing from the composability or PCIe switching. So this is just to summarize basically kind of what we call here sensitivity of these workloads to composable system topology features. So the figure here on the left shows the sensitivity to GPU disaggregation. As you can see here, as the models get larger, of course, communication here becomes bottlenecks. And even, the differences that we see between GPU to GPU, local host, and then through the Falcon switch start making a big impact in terms of the overhead. In terms of the storage disaggregation here, we didn't really see much overhead here in terms of having storage attached locally or disaggregated at the application level. So actually here we just scratched the surface. I mean, this is still a small system, a prototype of a composable infrastructure. But this design, we've shown here that through a composable system, we're extending the configurations options and virtualization for the system software level down to the hardware level. This also allows us to improve resource utilization, gives us much greater flexibility, and also decouple the lifecycle of the devices. In terms of the characterization that we've done for the deep learning benchmarks, we see that there is, of course, overhead involved with this PCIe switching. And we're also looking at what do we do to improve this and also provides a much higher performing PCIe switching, looking at protocols like CXL that Professor Chris mentioned. And this especially increases as these models are increasing. However, for large smaller models, modularity size models, the overhead is still acceptable at the expense of having greater flexibility. And of course, additional software level optimization can definitely help reduce further the PCIe switching overhead. So future directions here, we're looking to improve the design of the composable fabric, especially by making the PCIe fabric much more performant, increasing the speed, looking at protocols like the Compute Express Link protocol. And there is an ongoing collaboration with RPI. I mean, the previous talk also mentioned this. We're also looking to use this environment, especially to evaluate the new AI hardware accelerators. And this is in the context of the AI Hardware Center, looking at both, reduced precision and analog AI accelerators. And I mean, here, the evaluation that we've done only looked at one node. We're looking to do this at a much larger scale, looking at distributed applications with many nodes. and also how the composability affects when we're going larger scale. And in addition to this, also, there is a lot of interesting work here around how do we know what's the right level of resources for different applications? How do we determine, looking at historical data or logs from workloads, what's the right, computation versus acceleration versus, so we need to use AI technologies and also couple that with system level monitoring and so on to be able to automatically recommend optimal system level topologies in an environment like this. So I'm just going to end with this. This just, shows some of the benefits that we believe in a system like this. And we also believe that this design has the potential to be very helpful in the infrastructure for both cloud computing and high performance architectures. We've only scratched the surface here, so lots of interesting work ahead of us. Thank you. Happy to take any questions.
Thank you, Kautar. Any questions? Feel free to unmute yourself and ask a question.
There's one question, Kautar. So is on this composable systems, is scheduling and resource allocation is an important issue, right? Like where you should put the GPUs, how much is the GPU affinity affects the performance, because different deep learning models have different sensitivity to GPU affinity, whether they're on the same PCIe switch or on a different
Definitely,
host, right? So are you guys thinking around that line also?
Yes. Yeah, that's also what I mentioned as part of our future directions, to be able to understand, like the sensitivity of these workloads to these different architectural level characteristics, like the GPU affinity, the communication, and sometimes does it really make sense to have NVLink, or when does it make sense or not sense, depending on the application, the phases the application is going through. So this is a system basically that would allow you to study all of these different components and how these things play together, and which components you need maybe to invest in more in optimizing or improving, and where basically the big bucks of the buck will help you in terms of return of investments at the application level.
And there's one question that will this be offered on cloud, or it will more, what is the idea? Like this will like composable.
We have kind of a small prototype system that we're offering to our AI hardware center members for experimentation. Within IBM Research, there's a lot of work also that's working on how do we make this as part of data centers to help with resource utilization and so on. So the idea is to make this kind of one of the backbones of the implementation of data centers in the cloud.
Thank you.
Okay, great. Thank you, Kautar, for the great talk. So yeah, thank you very much. And now it's back to Parijat and Danilo.
Yeah, thank you. Thanks, Jairam. And so we are at the end of our workshop. And so this is the time to thank everyone. And firstly, I would like to thank the participants, right? Because they stayed, we worked across 3 different geographies and three different time zones, and we had good attendance throughout the workshop. So, and also our speakers, both invited and contributed speakers. So it was a great talk. We had great speakers, and we learned from at different levels of the stack of the deep learning, right? And going at the very low hardware level up to federated learning level. So it was a wide gamut of things that we saw. So it was interesting. And then I would like to thank all my colleagues who helped me in organizing who helped us in organizing this workshop. So Stacy Patterson, she our co-chair, Danilo and Jairam and Yogesh for handling everything from the program to the logistics. They made this experience so smooth. And also Ashish and Vinod for their mentorship, because they are the one who started this workshop. And so Vinod, so it was good. And ultimately, and Anirban and Federica for doing the publicity of this workshop and making sure that the call for papers, calls for participations, everything was posted on the right channels so that we can attract and we can our workshop is known to the community to a large extent, right? So having said this, I would like to thank everyone, and we are at the end of the workshop. So hopefully you all enjoyed it, learned it, and I would now like to say if Danilo and Stacy they want to say any words, few words, please, or yeah, and anyone in the organization committee, please go ahead.
Stacy, please go first.
I don't have too much to say other than thank you very much to everyone for attending. It was really interesting. And also thank you, Parijat, for inviting me to be a part of this and pulling everything together, organizing the meetings and also for everyone who's participated in everything. It was a really great experience, and I hope I'll get to work with you all again.
Yes. And actually, yeah, I join thanking you all with my colleagues. I think the topic we are very interesting. We had very nice contributions. We thanks again all also the invited talks because they were very high quality, and it's really a pleasure. We really hope that we can organize these meeting in person the next year. So that's the second year that we go virtual, but hopefully by the next year we will have really the opportunity to meet each other. Okay.
Sure. Yeah. Hopefully next year we will have it in person. Yes.
Yes, I hope so too. And the one thing I would add is it would be great if every one of you keeps the workshop date in mind and contributes again next year. I hope to see a doubling of the papers submitted, and that's something I'm really asking everyone who attended today.
Yes. Great. Thank you, everyone.
Thank you.
See you next year, everyone. Okay. Yes.
Thank you. Thank you.
Okay.